I'm going to draw it. So what you were looking at was a sort of a vector problem where you're trying to get from the door to the bed. Let's do the bed. The bed looks something like this. That's the pillow. And you took kind of a strange way to get there. And if I recall, you went, let's see, 1 meter, 30 degrees south of east. So you went like so. We'll call it like that. And then you kind of went west of north, which was the wrong way. Then you went straight east for a little ways. And then you went a bit south of east, like this. So, you know, roughly that's the path that you took to get there. And the question is, were you close enough to the bed to land on it when you fell? So what's this distance? That's what you're looking for, okay? Now, I don't think anybody got all the way through the problem before you left. Did anybody get? Okay, cool. Well, we're going to do it. I'll do it up here. I'd usually like to see what you guys are working on, but I want to cruise through it so we can get going on to new and better things. So I said the distance here was 4 meters. So let me break down how I went about solving this problem. I actually did this in my notes. I don't want to do it that way. I'll just do it again. Okay, so the way that I looked at this is I broke it up into 4 parts. And I sort of alluded to maybe you wanted to do this as you guys are working on it. But what I did is I said, okay, well, there's 4 different paths, so let's look at 4 separate parts. Let's sort of break it up. And whenever we're dealing with vectors, and these are all vectors, these are all displacement vectors, whenever we're dealing with vectors, we want to break up the vectors into their vector what? Components, right? Good, you're learning some physics language. So what we're looking at here are a bunch of different vectors. So I'm going to draw them out sort of bigger. There's 1. Number 2 is sort of this way. Number 3 was straight to the right. And number 4 was in this sort of direction. And then I'm going to, of course, label the information that I have. So the first one I knew was 30 degrees below east. All right, 30 degrees south of east, and the length of this guy was 1 meter. Number 2 was 2 meters, so these are obviously not to scale. And we were working at an angle of 10 degrees west of north. All right, this guy was 1.2, not 1.3, I just said it. 1.2 meters, and that's due east, so there's no angle there. The angle is 0. Call theta equals 0 in that case. And then finally, we had 0.8 meters at an angle that was south of east. So what is that, 70 degrees? 70 degrees south of east. All right, so that's what we're looking at. All we want to do in each of these cases is break these guys up into their vector components. So what does that mean? I need to draw the vector components are going to be parallel to the x and y axis. So I'm going to label an x and y axis here. X is that way, y is straight up, sort of like normal. So what I'm looking at is to make a bunch of right triangles. So here's one right triangle where this is the x component of my first vector, and this is the y component of my first vector. Right? So in order to get the x component, let me give myself a little bit more room here. Let's do one at a time. So the x component, this side up here, how would I calculate that side? I'm going to call this 1x, which is sort of weird, but fitting. All right, so 1x is 1 meter times the cosine of 30. Right? 1y is equal to 1 meter times, if it's not the cosine, it's probably sine of 30. All right, so that's how I break up those components. What are those numbers? Cosine of 30 is like root, that's that weird root one. 0.87. And then this must be 0.5 meters. All right, so I've got the first one done. Do the same exact thing for the second one. Now I'm looking at a right triangle that looks like so. All right, again, the red designates those must align with my x and y coordinate axis, so up and down, left and right. So 2x, what's that going to be? Well, it's got to be 2 meters times something. Sine or cosine? Good. Sine of 10 degrees, all right? Don't always associate cosine with x. That's a really common mistake, all right? To say, oh, x direction, it must be cosine. That's not the case. It depends on how you draw your triangle. In this case, it's the sine because we're trying to calculate this side. That's the side that's opposite of my angle, so it must be sine. All right? 2y then must be 2 meters times the cosine of 10 degrees. I need some help on this one. These both. This must be 0.35. And what's the y? 1.97 meters. That sounds right from my recollection. All right, good. 3 is easy. The angle is 0, so then 3x is just the length of my vector, 1.2 meters, and 3y is zippo. All right, so then 4, once again, I draw a triangle. Kind of goes out here. There we go. Sorry, it's kind of overlapping my writing. So again, this is the x side, up and down is the y side, so 4x must be 0.8 times this, we got the cosine again, the cosine of 70. 4y is equal to 0.8 times the sine of 70. Once again, I need a little bit of help. 0.27? 0.75, thank you. Okay. Where's the mistake? There's a couple mistakes. All right, so I have some sign errors. I did everything positive, but that can't be right because sometimes the arrow's going to the right, sometimes it's going to the left, sometimes it's going up, sometimes it's going down. So starting over from 1 here, I've got positive numbers. Is this positive or negative 0.87? Positive, because my x-axis I've defined is going to the right. This side is going to the right. So that's got to be positive. 0.5, is that positive or negative? Negative. Right, good, it's negative. That's too high. All right, the second one, my x, now here my triangle is, or my vector is going a little bit to the left, so the negative sign goes on the x component this time. The y component, we're pointing up, so that's positive. These guys are both positive, or 0 is 0. And then finally with the x, or with number 4, my x direction is positive. My y direction is negative once again. All right, so now I've broken everything up into their x and y components. Now what I can do is, what I'm after is the total displacement. I'm after the net displacement. I'm after something that goes from here to here. It's kind of not too bad. I'm going to call this, I'm going to call it the displacement delta R, to use your book's language. All right, the net displacement. The way that I get that is I just need to add together my vector components, just like the numbers that they are. I'm going to do that in both the x and the y direction. Right? So if I just do the x first, what I have is 0.87 meters minus 0.35 meters plus 1.2 meters plus 0.27 meters. Okay? While somebody's calculating that for me, I'm going to go ahead and do the y direction. I'm adding these together, all the y components together just like normal numbers. Negative 0.5 meters plus 1.97 meters plus 0 meters minus 0.75 meters. All right? I still hold the x and y components to be independent. Sometimes I'll do this in the table. If it helps you to see it, do it in a table by all means. All right? Somebody give me the answer, please. 1.99 meters. That sounds right from my recollection. Okay? So now I have a vector defined. Delta R, which is what I called it, in our notation that we sort of were using to start is 1.99 meters, comma 0.72 meters. Remember this x, comma y notation. That's my vector y. Right? And so I can sort of get an idea now what the answer is. I want to know if I'm close enough to fall onto the bed. Well, the bed is 4 meters away, right? So how close am I? Or how far away am I? How far away am I? In the x direction, I'm 4 meters minus 1.99 meters. I'm going to round that to 2. 2 meters away. All right? And the y direction, The bed, I didn't really say what position it is in the y direction. We'll just say it was 0. So the bed is at 0 meters. I went 0.72 meters, so I am negative 0.72 meters away. All right, so looking at this answer already, I'm thinking I'm probably not going to hit the bed. I'm going to spend the night on the floor. All right, but we could do one more step here if we wanted to. We could write this vector in another way. So the way that I do that is I calculate a magnitude of my vector. That's equal to the square root of 2 squared plus 0.72 squared. So I rounded 1.99 to 2. All right, so this is the magnitude. 4 plus 0.72, it's 2 point what? 2.12. All right, and that's after the square root's been taken. All right, so my magnitude is 2.12 meters. My angle is, how do I calculate the angle? Let me draw the picture really quick. So we started from the origin here, somewhere at the doorway. We traveled 1.99 meters to the right. We traveled negative 0.72 meters. I just calculated the magnitude of this guy. This is delta R. And now I want this angle theta. All right? So how do I get that angle theta? Sounds good. You can use any of them because you know all three sides. We can choose the tangent. That's fine. And it's 0.72 divided by 1.99. And what's that angle? 19? 19.9 degrees. All right, so now I can write my vector delta R is equal to 2.12 meters at 19.9 degrees, and that's south of east. All right, so that's another way to write the vector. Usually this is how I want it, but this is an acceptable notation as well. If I don't specify, then that's fine. All right, now, is everybody clear on, so down here in this, when I was doing this theta calculation, I didn't use a negative 0.72, even though we had a negative 0.72 in our answer, in our first part of our answer.
So, yeah.
Oh, was it positive? Did I switch up on us? Oh, I'm sorry, I did switch up on you. Thank you. I'm sorry. I decided to throw that one in there incorrectly. So this was negative 0.72. Yeah, I'm sorry. I've got this sort of backwards. So this should have been positive because I should have done. All right, I should have switched that. So that's my mistake. So we were just calculating the distance from the bed, and all of this should have been swapped. Because I wanted to figure out, basically what I did here is I was taking a look at what would happen if I move my origin, basically. So I'm 2 meters to the left, so that's why there's a negative sign, and then this would have been 0.72 meters to give me a positive. So 0.72 meters up. So thank you for catching that. And that, of course, changes this picture. To something like this. Or that's theta, okay? So the numbers are all the same. I just had to change around theta a little bit, and that becomes north of east. All right, sorry about that mix-up. Okay, but still, the same question would have held. Because I defined my angle to be this angle, these sides, when we talk about right angles, we usually don't have negative lengths for sides, right? So whenever you're referring to an angle, we're using the positive numbers. I'm going to get a little bit more confusing later when we start to always, in physics, we typically define a positive angle as going counterclockwise from the positive x-axis, which you probably did in geometry or trig, if you remember. So at some point, we'll probably start to do that, in which case then you might have to use a negative sign or something like that and get a very big angle. right? So watch out when you're dealing with problems. Sometimes the questions in the book or on an exam will ask you, what is the angle from the x-axis positive is counterclockwise. So you can imagine then if in the example where, let's say, you're basically looking to see the angle between these two vectors. If we define this to be positive, then our angle, which is this big thing here, would be theta is something like, I don't know, that's let's call it 200 degrees. Right? There's another way I could write that, though. I could write that as a negative. So I could say theta is either 200 degrees or negative 160 degrees. Right? Because 360 minus 200 is 160. Right? Does that make sense? Everybody seen that before? Seen that sort of thing in your math class? So these two would be acceptable answers in this little example here. Okay, but typically we define an angle as positive being counterclockwise from the positive x-axis. In this case, I was just really specific because we have the cardinal directions, and so we can do that. Any questions on this example? So far, so good? All right. Okay, so I want to, this is all technically part of Chapter 3. I sort of treat Chapter 2, or 3 and 4 as one big mega chapter. But just to make sure we're on the same page, in your book, they get into a little bit of notation when they start to talk about the difference between position and velocity and acceleration vectors. So I just want to go through that really quick, and then we'll move on. So now that we're working in 2D, it sort of doesn't make sense in some way to use the same sort of notation. So let's go back and revisit position. Wow. In 2D. All right. So should we do this? Let's do it. Let's do it in the form of an example. But you've already seen a little bit of a different notation. And you saw that in the context of displacement. But now, instead of writing the position in general as something like x or something like y, typically what you're going to see is the position, the way that we write position in physics language is we use r. R is how we refer to position. And if you have a position vector called r, you can write it in terms of its components, x and y components. All right? And the way that you do that, I'm going to break out something a little bit new here, is like this. Has anybody seen this before? This notation before? All right. That's why we're talking about it. So you might notice two new things here. This little I thing and this little J thing with some sort of funny hat. All right? These things are called unit vectors. All right, unit vectors. The whole purpose, the whole point of unit vectors is so that we can write down a direction. These things are just directions. That's all they are. The I hat and the J hat, those are just telling me that this Rx thing, the magnitude, that's pointing in the x direction. And this magnitude, R sub y, that's pointing in the y direction. So I hat, technically what I hat is, it's a vector that has a length of 1, all right? But its direction is along the x-axis. Right, that's what I hat is. And the reason it's called a unit vector is because it has length 1. It has a unit length. So that 1 applies to no matter whatever unit you're using, it has 1 in that unit. Okay, so when I multiply I hat by some magnitude, I'm not changing the actual magnitude of that vector component. All I'm doing is telling you which direction it's pointing. All right? The exact same thing holds for the j hat. The j hat is the same thing. in the y direction. Okay? I don't want this to be more confusing than it is. It's actually really, really simple. They're just little tiny vectors that tell you which direction. They assign a direction to a magnitude. All right, so if I write down then, let me do a little bit of an example up here in the corner. All right, I'll draw a position vector. I'll draw it to this point right here. All right, that position vector, I can write that in a couple different ways. I can write that, like we've seen so far, as in the x direction it goes 1, 2, 3. I'm trying to label my axes. And it goes 2, positive 2 in the y direction. That's one way to write that. Another way to write that is 3I hat plus 2j hat, where I use my unit vectors. Okay, so it's just a different notation. These things have a magnitude of y of 1 each. They just point along the x and y axis. All right. This is the most common way that we denote vectors when we're using components. So you'll see this time and time again. All right? Is that okay? All right, good. So that's an introduction to unit vectors, and we're going to use those again and again. Now, so we talked about position. The next thing up the ladder then is displacement. All right, so if our position is an r, then our displacement now becomes a delta r. Again, this is sort of semantics. It doesn't really matter. This is just what's in your book. This is typically how we write a vector, the way that we designate a vector in 2D or 3D coordinates, but it's not really all that important. And just like before, we can calculate the displacement by taking the difference between the initial and final positions. Velocity doesn't really change. It still gets a v. The only thing that changes is the definition, which is the displacement divided by time. So we get a delta r instead of a delta x or a delta y. Right? Now let's look at an example using velocity so that we're comfortable in doing that. So I'm gonna switch over here and use the keyboard because it's better. To make that 18 point a default. All right, so you observe a bird, something pretty simple. A bird that is initially at a position of 3I hat plus 2j hat. I'll add the hats in just a second. And then 5 seconds later, it is at 5I hat minus 1j hat. All right? Now these aren't unit vectors until you add in little hats. If you just see i's and j's, then somebody's trying to trick you. So there's a hat, there's a hat, there's a hat, there's a hat. Beautiful. You can even see it on the board. All right. So what we have here then is a vector problem, a 2D problem where we want to calculate the velocity. So my velocity is a displacement over a time, so let's calculate the displacement first. So delta r. All right, I'm going to write this out just like I would in my physics job. All right, so delta r is going to be r final minus r initial. All right. So my final position is 5I hat and then minus 1j hat. All right. My initial position is 3I hat, 2j hat, like so. So I've given you this. What is my result going to be? All right, good. So that's what I wanted to hear. You can only, just like before, just like in our previous example, you can only add together components that are in the same direction. That's what we've done here. This vector is already broken up into its components, right? We have I hats and j hats. Those are the vector components. So I can only add together numbers that look alike. I can only add together I hats with I hats and j hats with other j hats, right? So one way to do this, I'm going to be super thorough and write down one way, how to do this very carefully. I'm going to combine the I hats, so I'm going to stick the I hat in front, just like I'm factoring out an I hat, right? And so I get 5 minus 3, and then I'm going to add the j hat components to my vector. There's a negative 1 here, and then I'm subtracting a positive 2, so I get a negative 2. All right, so I can only add and subtract like components of vectors. And so the result becomes 2 I hat. This is negative 3 minus 3 j hat. All right? I only added and subtracted the same components. So if I draw a picture then, I could draw the picture like so. I go 2 to the right. I go negative 3 down, and that's my displacement vector. Okay? All right, so now I want to calculate the velocity. That's what I'm really after here. So, okay, now what is the velocity? Well, I just had this definition. It's delta r divided by t. So v is delta r, which I just calculated to be 2 I hat minus 3 j hat, and then I divide by delta t, which is just 5 seconds. So in dividing this, I'm just dividing scalars. I can't do anything tricky with my I hats and j hats. Those are going to be in my answer because it's a vector. So what I get is 2 divided by 5 in the I hat, or 0.4 meters per second in the I hat direction, minus 3 divided by 5, which is 0.6 meters per second in the j hat. And that's my answer. Okay? And once again, I could go through the part where I calculate a magnitude and an angle, but this is fine to leave it in this form unless I tell you otherwise. Right? So I have a vector here. I'm using unit vectors, as we'll try to do more often than not. Once again, I hat and j hat, length 1. They don't change the magnitude at all. They just tell me the direction. Okay? If I were to draw a triangle, would it look the same as this triangle? Well, it's a similar triangle, right? Because the velocity vector and the displacement vector point in the same direction. So my velocity vector is, instead of going 2, I go 0.4 to the right, and I go 0.6 down, and then this is my magnitude of my velocity vector. Okay, all I've done to get velocity is I took my displacement and scaled it, because time isn't a vector. So I didn't change the direction at all. I just scaled the vector. Okay, so the two triangles are similar. They just have different length sides. It's a different size triangle. Okay, and then the last thing that we've gone over in 1D was acceleration. Acceleration doesn't look any different at all than what we've seen before. A is equal to the change in velocity divided by the change in time, just like before. There's really nothing new here. We'll do a really quick example just to be thorough. I think I like using this guy. So a car, it's traveling at 20 meters per second north after taking a curve for 4 seconds. It travels at 20 meters per second west. And I want to know that should be a little w. What is the average acceleration? So once again, I'm asking for the average acceleration. In the previous example, we calculated an average velocity, not an instantaneous velocity. All right, a car is traveling 20 meters per second north, which would be, let's go with the color here. No, that's fine, but I need the brush. I have the brush. All right, so it's going this direction. There's the car. You know I'm great at driving cars. Then it takes a curve. That's pretty bad. And ends up traveling to the west, still at 20 meters per second. So this is 20 meters per second over here. All right, now I want to know, and this curve takes 4 seconds. So let me ask you this. What's the acceleration of this car? All right, who says 0? Who says not 0? And a lot of you say, I'm not going to decide. Okay, the acceleration of this car is not 0. Somebody tell me why. The direction is changing. Acceleration is a vector, all right? A vector can change if the magnitude changes or if the direction changes, all right? So this car isn't speeding up at all, but the direction is changing, and so we say that it's accelerating. It's really important to understand the difference right now because, again, like everything we do in this class, it's just going to get more complicated later. So yes, the car is accelerating even though its speed isn't changing. All right? Which direction is it accelerating? Well, okay, well, negative, we haven't, if I draw an axis, I'll draw an axis. I'll call this positive x and this positive y. So you say negative what? Negative x, so you say it's accelerating to the left? Anybody else say something different?
Accelerating at some...
You're saying, you're saying down?
Northwest-ish.
All right, well, you know what? I'm talking about the direction of the acceleration. It's a vector, so it's got to have a direction. So let me write this down. We've got some people saying negative x. That's not even close. That's better. So is it this direction? Is it this direction? And somewhere in between. All right, so we sort of have 3 choices maybe. Maybe you could imagine more. I'm going to stick with those 3. All right, but you know what? We can figure it out. So let's figure it out using doing the problem. Okay, so we have our delta v is going to be our final velocity minus our initial velocity. That is an f. All right, so the final velocity is 20 in what direction? In terms of unit vectors? Huh? All right, first it's negative and it's in the I hat. Good. So that's v final. If I want to be super thorough, I could say it doesn't have a velocity in the j hat. All right. I'm going to subtract off my initial. It's not moving in the x direction, so there's 0 in the I hat. And then it's got a plus 20 in the j hat. All right? If I do the very, very difficult math, I get negative 20 I hat minus 20 j hat. All right, that's my change in velocity. Negative 20 I hat minus 20 j hat. So to get acceleration, I just need to divide that by time. Minus 20 I hat minus 20 j hat. Divided by time, I said 4 seconds. So acceleration then, according to my math, is negative 5 meters per second squared in the I hat direction minus 5 meters per second squared in the j hat direction. All right, if I draw that,
I have a question.
yeah.
So, for the initial... Oh, never mind. I just answered my own question. Never mind.
Okay.
I saw something that was wrong.
Okay, that's fine. I certainly could have done something wrong because.
No. I didn't see the negative sign in the beginning of the v final.
Okay. Yep, it's hidden there. All right, so if I draw this, here's my axis. My acceleration vector goes, it points negative 5, like so, and negative 5 in the j hat. So my actual vector points in this direction. All right? Does this make sense? Why is that okay? Is that funny? So can somebody explain to me why that is based on, these two? What's going on here? Can somebody explain that to me? Why is our acceleration pointed in between the x and the y and not along one axis or the other? Patrick?
But I would assume because of the curve, like when the car is about to take the left and whatever,
All right, it is curving. This is now, it's an average acceleration. Yeah.
When you go to take the corner, the car is slowing down.
Okay. Good, right idea, but when you say slowing down, I think what you're really thinking about is one of the directions. Yeah.
Is it because are you having positive acceleration before direction when you're going up, and then the opposite direction going that way?
Okay, so you're sort of getting in the right idea. So let's just take a look at each direction independently. So is the car speeding up or slowing down in the y direction? All right, it's slowing down. It's going from 20 to 0. So clearly in the y direction, the car is slowing down. In the x direction, it's doing the opposite. It's speeding up in the negative x direction. All right, so initially in the y direction, it's going 20. Later on, it's slowed down to 0 in the y direction. Initially in the x direction, it's not moving at all. Later on, now it's going negative 20 meters per second in the x direction. So its speed is changing in each direction individually. And when we bear that out in the actual acceleration vector, that's what's reflected here. We're saying, okay, it's slowing down in the y direction. It's accelerating in the negative x direction, so it's sort of slowing down if you want to. Nope.
No.
The speed of the car is always 20 meters per second. It doesn't change at all. Okay? But yeah, the speed in the x direction is 0 initially. The speed in the y direction is 0 at the end. But the speed of the car itself is always 20. Just like when you take a turn, cruise through the intersection, I don't know about you guys, I don't like to hit the brakes when I take turns. So, your speed remains constant. Right? You're just changing direction. And so that means that you're accelerating. In this case, because we make a 90-degree curve, our acceleration vector, our average acceleration vector, is at 45 degrees. What's our instantaneous acceleration vector? What angle? You mean over here? Well, how could that be? In order for it to be that over here, it'd have to be speeding up in the y direction and speeding up in the x direction. That's all right. I like shot in the dark. Shots in the dark. What do you think? What's the direction of the instantaneous acceleration vector? Sort of a trick question. Yeah, it depends on the instant that I'm asking about. So initially, right at this point, the acceleration vector is sort of pointing down. Okay, and then as we go through time, as the car turns, the acceleration vector turns. I'm sorry, I said that exactly wrong. Initially, the acceleration is pointing to the left here. And as the car turns, the acceleration vector starts to tilt downwards. All right? We'll come back to this, but whenever you have circular motion, whenever you're making a circle, and this curve is just part of a circle, the acceleration vector is always perpendicular to the velocity vector. So right here at this point, acceleration is, try to do a better one, is this direction. So this is A instantaneous. And here at the end of the curve, while it's still curving, but right at the end, our acceleration vector is pointing straight down. All right? And so in the average sense, if my speed stays the same, well, the average of these two arrows is right in the middle there. Okay? All right, so now we're going to really talk about kinematics now that we have these sort of basic definitions out of the way. Now, when we're attacking problems in 2 dimensions, and I said this last Thursday, we use the same physical laws. All right, the same laws that we used in 1D still apply to 2D. The only difference is now we're going to solve two problems. Instead of 1D. Right, that's the whole key to solving two-dimensional kinematics problems. Right, but those equations that you learned before, they still hold, they still apply. We're just going to do them twice, sort of. All right, so let's do this in the context of an example. I think that's the best way to learn this stuff. All right, so example. Let's do the spaceship example. I'm definitely going to want to text this out. All right, so I like spaceships, as you guys know. You flying. You are flying. You're flying a spaceship, and you're going 25 kilometers per second in the x direction. And then as you're going that speed, you fire the thrusters. And that results in an acceleration. And that acceleration is 3 kilometers per second squared. Oh, I can't, there are no shortcuts. All right, you're going to know what I mean when I do it like that. That's a second squared in the y direction. I'll have to try to make a keyboard shortcut for squaring something. All right, so you're flying a spaceship 25 kilometers per second in the y direction. You hit the thrusters to give yourself an acceleration up or in the y direction. All right? The question that I have is how far has the ship traveled after 20 seconds? All right, how far has the ship traveled? So what I'm really asking about is what is the displacement of the ship? All right. Still big enough you can see it okay? All right, so this is a 2D problem. We have motion in the x direction, which eventually will end up being motion in the x and y direction. So let's see. Let's follow our steps. So I had some steps outlined before when we talked about how to solve kinematics problems. The first was draw a picture. All right, I'll do that. We have a spaceship traveling in this direction, but eventually we're going to fire the thrusters so that we get an acceleration upwards at this point in time. All right, and what that means is that the trajectory must start to change. We're introducing a vertical component to our velocity. Our acceleration is perpendicular to our initial velocity vector. We're going to curve upwards. Okay, so that's what the picture looks like. And eventually we're going to be heading in some direction like so. Our velocity vector is here, and that's 20 seconds later. Okay, so that's the picture. With the picture, I'm going to throw in some axes. I've already actually done this because of how I drew it, but we want to make sure we're clear. X and Y are labeled horizontal and vertical just like normal. All right, so 2 is label what you know. We have 2 dimensions now. So the way that I always do this, I like to make tables. So I'm gonna do this. Let me write down what I'm gonna do. I'm gonna do unknowns and knowns. So I'm gonna make a little bit of a chart or a table. So I've got 2 dimensions, so I have a list for each direction. Right? This list looks just like the list we were making before. We just have to make 2 of them. All right, so just pulling things out of my head. Our initial position in the x direction, our initial x position. What do you think? 0. All right, again, sometimes the hardest parts of these physics problems is making these lists. I didn't give you very much information in this problem. I gave you a time, I gave you an acceleration, I gave you a velocity, but we're going to have like 10 things here or more. So figuring out what is the key. I can choose to put my axis wherever I want. So my origin, I'm going to put right here when I turn on those thrusters. Okay? That's my origin. So at the origin, x is 0, and I guess I could fill in, not x, fill in y naught, and that's going to be 0. Okay? Our final position, I don't know what that is. That's what I'm after. All right? My initial velocity in the x direction. Look at this triple or double subscripting things. Oh, God. All right, so initially, I'm traveling at 25 kilometers per second in the x direction. My initial velocity in the y direction, what's that? It's 0. All my motion is going to the right. All right, my final velocity in the x direction. Who can tell me that? I don't know. It is still 25 kilometers a second. So it is not going to be going straight up. Why is it not changed? I gave you an acceleration, constant acceleration of 3 kilometers per second squared in the y direction. I didn't tell you there was an acceleration in the x direction. There is no acceleration in the x direction. Ax equals 0. So if there is no acceleration, then the velocity can't change. All right, in the x direction alone, all right, remember these aren't vectors now because we've broken them up into their components. So our x component of the velocity vector doesn't change. That means the x component of the acceleration vector is 0. Okay? Again, this is the hardest part. Once you make this list, you're good. All right, I can do similar things for the y direction. So Vy, the final velocity in the y direction, I don't know that. Right? Because we're accelerating. We're starting from rest and we're speeding up. And then what's my acceleration in the y direction? Yeah, it's what I gave you. So 3 kilometers per second squared. All right? So I've listed everything except for one thing, time. All right? Time is the great equalizer. Is that a saying? I don't know. All right? So time, the key to these problems, the key to all of these problems is that time is the thing that links together x and y. All right? The motion in the x direction is completely independent from the motion in the y direction. But for an object, for a single object, the thing that's linking these two directions together, that's time. So it takes me the same amount of time to go from x initial to x final as it does from y initial to y final. Because it's the same object. It's not splitting up and going different directions. All right? So time is 20 seconds, and that applies to both directions. That's the key. So what that allows me to do then, and this is something that's going to pop up time and time again, is if you know a lot of information in one dimension and you don't know a lot in the other dimension, typically what you have to do is solve for time using the one that you know a lot of stuff, take the time, and then solve for the thing that you're looking for in the other dimension. All right? This will come up a lot in the problems that you encounter in the homework and on exams. All right? So we're going to use time a lot. Now, this first problem, though, I'm trying to keep it a little bit simple, so we're actually not going to do that right away anyway. All right, so we already know time, so we can really treat the two dimensions independently. So the first thing I'm after then is I'm after the total displacement of the ship. So I need to know the distance traveled in the x direction, and I need to know the distance traveled in the y direction. All right, so in the x direction, we'll do that first. All right, the x direction, it's not accelerating. The initial velocity is the same as the final velocity. I just want to know the distance traveled, so I can write down this equation, x equals x naught plus VOx. Oh, I'm sorry, I usually do the x first. XO times time plus 1/2 AX times time squared, okay? Same equation we saw in 1D, we're just throwing in some subscripts, okay? This applies in the x direction now. There is no acceleration in the x direction, so that term goes away, and I'm just left with this nice simple equation. Right? X naught also 0, so our final position is just going to be equal to our initial x velocity times time. And I can just plug in my numbers. Was it 25 kilometers per second times 20 seconds. Not 2. So my displacement, or the distance traveled in the x direction, is 500 kilometers. Right? No different than when you did it in 1D. Like I said, we're taking one 2D problem and turning it into two 1D problems. So I've solved the first of my 1D problems. Now I need to do the y direction. Right? So in the y direction, I do have an acceleration. Again, I want to know the distance traveled. So I'm going to write down another very similar equation. I'm just going to subscript it with a bunch of y's. No. So y is equal to y naught plus vy0 times time plus 1/2 ay times squared. All right? In this example, my initial position is 0. My initial velocity in the y direction is also 0. So I can get my total distance traveled in the y direction by taking my velocity, or my acceleration, which is 3 kilometers per second squared. Whoops. And multiplying it by the time squared and then 1/2. And if you do that, you get a distance traveled of 600 kilometers. All right, so here's two 1D problems. Same exact equation that we used in 1D, nothing new here. All right? Like I said a million times now, the hardest part is making this list of information. That's the hardest part. Once you do that, you can say, okay, I've got one 1D problem, another 1D problem, just pick out an equation and solve. All right? The result then is we get a displacement that looks like this. I'll try to be reasonably thorough. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've gone 500 kilometers in the x. We've gone 600 kilometers in the y. Our displacement looks like, let's just use the line tool. That'll be much nicer. There we go. So that's our displacement. And I guess I can vectorize that. All right, and I'll call that delta R just for clarity. Okay, what does the actual trajectory of the spacecraft look like? Does it look the same? It's a curve. How does it curve? It starts off moving which direction? So here I am at the origin, starts off which direction? All right, it starts off going in the positive x, accelerates slowly in the y, and eventually will be moving faster in the y direction than the x direction. It has a constant acceleration. So Sean, you sort of asked if it'll eventually be going straight up. It'll never be going straight up, but you know, this thing is accelerating in the y direction. It's going to keep speeding up and speeding up. So while the x direction will always have this constant velocity of 25 kilometers per second, if nothing happens to the ship, eventually the velocity in the y direction will be really, really big, 1,000 kilometers per second, 1,000,000 kilometers per second. So eventually the vector velocity will look like that, the vector components, and then, you know, a little tiny x component. So yeah, I mean, it'll kind of look like it's straight up, but it'll never be perfectly straight up because it'll always have that little tiny itsy bitsy chunk of 25 kilometers per second in the x direction.